Hi guys, how is everyone doing? Today's lecture is about improper integrals. Let's get started now. In the previous chapters, like in chapter 5, 6, or 7, we have seen this form of integral, this one. Integration of function f(x) with respect to x, starting at a and ends at b. At this point of the course, we know that this form is definite integral because we have the upper bound and the lower bound definite integral. And we also know from the fundamental theorem of calculus number 2 that this definite integral can be calculated by using one very important formula, which is this. Definite integral equal to the antiderivative, which we use the big F to represent, evaluated at the upper bound, which is b in this case, minus another antiderivative, big F, evaluated at a. Since we use this formula a lot, I'm going to make a box around that. So we have seen this a lot in the lectures, in the homework, in the practice problems, and in many places. But let me tell you something. The ones that we have seen so far, they are all proper. Alright, so let's make a note here. The ones that we have seen so far, every one of them is proper. So far, they are all proper. That's the key word. Every one of them. Today's lecture is about something different. It's about improper integrals. The integrals that are not proper. Alright? So here's the main focus of today. Improper integrals. The first thing we are going to do right now is to learn about the difference between improper and proper and what differentiates the two of them from each other. So let's take a look at the next slide. In this slide, we want to answer one question. What makes an integral proper? What kind of things we have to look for, and we know right away the integral in front of us is proper or improper. Before we talk about that, let's take a look at the form that we need to focus on. That is this one, the definite integral. Okay, I'm going to keep things simple. The things that we have to look for when it comes to improper and proper is two things. Number one, something about the boundaries. The boundaries, and it's about A and B. Something about A and B is going to make a difference between proper and improper. Alright, the next thing that we need to look for is something with the function itself. Something about fx, about this one. So let's take a look at what about these two things that make the difference. Okay, so let's start with the proper ones. So far it has been all proper, this first box. So what about the boundaries? What happens here? So the condition here is that A and B has to be finite. A and B have to be finite. The boundaries have to be finite. Means that A and B cannot be infinity or minus infinity. You can make a note here, not infinity or minus infinity. So far you have never seen infinity in your integrals before, and that's why it's one of the reasons why every one of them is proper. Alright, the next thing is about the function itself. So let's take a look here. Number 2, condition 2. What about the function? Alright, for an integral to be proper, the function has to be bounded and defined. Let's take a look here. fx has to be bounded and defined on the interval of integration from a to b. Bounded and defined, it means that your fx cannot diverge to infinity or diverge down to minus infinity. It has to stay in bounds. All right. You can make a note here that this means that fx does not diverge to infinity or minus infinity on this range. And if you have these two properties, the boundaries are finite, the function is bounded and defined, then your integral is proper. All right. Now it's the turn for the improper ones down here. Improper, which is chapter 8. An integral becomes improper if it violates one of the two conditions that we had before. So let's take a look at the first violations about the boundaries. Number 1 right here. A and B was finite before, right, for the proper ones. Now for the improper, it's the opposite. It means that either A or B or both of them are not finite. So you can expect A or B or both of them to be infinity or minus infinity. Infinity or minus infinity. This means that in your integral, this sign of infinity is going to show up there. All right. Now that is the first violation, and we are going to call this improper integrals to be type 1. It's about the boundaries here. Now the second violation is about the function right here. For the proper one, function has to be bounded and defined. For the improper one, it's the opposite. Function is not bounded or not defined at some point on A or B. From A to B. What this means is that at some point in this range, your graph of fx is going to go very high to infinity, diverge somewhere, or it can go very low to minus infinity. You can say that fx diverges diverges to infinity or minus infinity at some point over the range. Okay, and this type of violation, we are going to call it type 2 improper integrals. Is the integral that becomes improper. Oh, I saw the typo here, improper. So type 1, improper, caused by the boundaries. Type 2, improper, caused by the function being unbounded. Right, so two types, and we are going to look into both types, but let's start with type 1. Once again, type 1 is about the boundaries are undefined. Boundaries are undefined. Or I should say are infinite. I'm sorry about that. Infinite. Infinite. Okay. Right. Let me fix that. Okay, so we are looking at the cases when A or B or both is not finite. So we are looking at three scenarios here. 1, A not finite. 2, B not finite. And 3, both are not finite. So let's take a look at all scenarios here. Number 1, right here, happens when A is infinite. Or in other words, A is, I should say, let me put this, A is infinite. But before that, let me put this formula down right here for you guys. Integration of fx with respect to x starting at a ends at b equal to antiderivative big F evaluated at b minus antiderivative evaluated at a. Let's put this in a box. Okay. Now, the first scenario is when a is infinite, and as you can see here, a is the lower bound. If it becomes infinite, it means that a is minus infinity. Alright, so what's going to happen here is, let's just put this into the notation. So in this case, we are going to have this simple integration just like before, fx and dx, but in this case the lower bound is minus infinity instead of some finite number, minus infinity. Since this is a problem, I'm going to put red right here, minus infinity, and the upper bound has no problem, so we put b as usual. It can be any number, finite number. Alright, so that is scenario 1. The lower bound is minus infinity. Now, scenario 2 is when b is infinite. So what happens here? As you can see here, b is right here, the upper bound is infinite. It means that b is positive infinity. So in terms of integral notation, you are going to have this. There is no problem with the lower bound. We keep it as a. Fx the same, dx. But the upper bound becomes infinite, and we have this. Scenario number 2. Okay, now scenario number 3 is when both a and b are not finite. So here, number 3, a and b are infinite. So as you expected, it's like combining 1 and 2 together. A is minus infinity and b is infinity. So in terms of integral, in terms of notation, we have two problems here. The lower bound is minus infinity and the upper bound is plus infinity. And the rest, no problem. Okay, 3 scenarios. Lower bound, upper bound, and both. Alright, and looking at these scenarios, they can be a problems when we try to use this formula to perform the calculations. The reason for that problems is because in order to use this formula, we have to evaluate this antiderivative at b, right here, and at a. F has to be evaluated at the boundaries. And as you can see here, these scenarios has boundaries that are infinite, which means that if we use this formula, we have to plug in b would be infinity positive, and a would be minus infinity right into the formula. And when you plug this kind of symbol into the formulas, infinity, it can be a problem because infinity itself is not a number. And you plug in, sometimes it's not defined, and sometimes it's just hard to perform the calculation to find the value of that. So we need something better. We need a better notation to make it more clear and more manageable. So here's how we do that. Alright? So if you don't do anything, minus infinity and infinity goes into play. So we need a better and more clear notation. So let's take a look here. So instead of having just minus infinity in the integral, we are going to do something different. All right, here let's transform this into something that is better defined. So everything is the same. Fx, this is scenario 1, b, and before we have this problem, minus infinity. So here, instead of using minus infinity, we are going to use a, like usual. But we can't just leave it like this because a is something special. So we have to put a message to tell that this a is not just any number. It's a number that is really large negative. So we can do that by putting this limit right here when a approaches minus infinity. So in terms of meaning, it's the same, but when it comes to calculation, it's more clear. All right. Now we are going to do the same thing for scenario 2 and scenario 3. This one, let's change that. So instead of having the original integral, we are going to transform it to something a little bit different. Fx still the same, dx. The lower bound a doesn't have any problem, so leave it. The thing that we want to change is this, infinity. Hard to deal with, hard to perform calculations, so we are going to change it to just regular b, just like in the formula. But then this b is special, so let's put a message right here. This b, not just any b, but it's a b that approaches positive infinity. All right. Okay, now for the last one, the last scenario, we have two problems, one at the lower bound and another one at the upper bound. We cannot just use one limit to deal with both of them at the same time. So we have to do something first, and here's how. So I want you to take a look here. We perform the integration from minus infinity to infinity. This is what happens. The first thing we are going to do here is to split this integral into two parts. So I'm going to pick one point, let's say any point here, point C, right here, and I'm going to split this improper integral, scenario 3, into two parts. So let's take a look at the first step here. The first step is to split it. This is going to be equal to, the first part is the integration from minus infinity to this particular point C, any point you want. So it's the integration of fx dx starting at minus infinity to C plus another integral, and this is going to represent this integral starting at C to infinity. Here we have starting at C to positive infinity, and here we have fx and dx. Okay, so at this point you might notice that this first one has the form of scenario 1 when the lower bound is minus infinity. This is scenario 1, right? And this one, this integral, is the improper integral with this problem, upper bound, and that is scenario 2. So with this 1 and 2, we can use what we know, what we have done before, right here. So this, I'm going to apply this this work down here. So instead of having this minus integration, minus infinity in the integral, I'm going to use limit instead. Limit of a goes to minus infinity. And this, I have a to be fx dx. Sorry, one mistake. In this case, not d, it has to be c. Okay, now for the second integral, I'm going to use this scenario 2 to replace here. So here, integration start at c integration start at c, ends at b, but not just any b. It's a b that approaches infinity, right? Fx dx. Once you arrived at this form, or this form, or this one, once you got to here, all you need to do is to perform the integration as you normally do. Alright? This type of notation is more clear. Alright? So let's use that in some of the examples in the next slide. Okay, so here we have 3 examples, and it shouldn't take long to finish this. So let's try to do this quickly. All right. So let's take a look at example 1. I look at this. This is just another integral, but then I notice that the upper bound of this integral is infinity. So this is definitely improper. And improper because of the boundary goes infinite. So this is going to be type 1 because of the boundary. And this is the upper bound that goes infinite. So this is scenario 2. Type 1 and scenario 2. Okay, so the first thing I'm going to do here is to change the notation from having infinity in the integral to having limit instead. So I need to save some space, so I'm going to start here. Okay, so here, instead of putting the infinity into the integral, I'm going to do something different. Integration 1 here, no problem, 3 over x dx. What I'm going to change here is to change the infinity to be just b, and then put a message right here. This b goes to infinity. Alright, and after that you just perform the integration normally. So this integration of 3 over x, it becomes 3 ln of absolute value of x, and you have to evaluate this at 1 and 3, at 1 and b. And don't forget that we still have the limit right here at the front. Limit of b goes to infinity. So let's perform the calculation here. Limit still here, b goes to infinity, and here we have 3 ln absolute value of b minus 3 ln of 1. And as you can see here, ln of 1, that's going to be 0. So all of this goes to 0. So in the end, you have this limit of 3 ln of absolute b, and b goes to infinity. B becomes really, really large. So this is going to go to infinity, and as you can see here, this limit is going to go to infinity as well. So in this case, the result that we got in the end is infinity. So we can call this result, this integral, divergent. Or you can say it diverges to infinity. Okay? So there is another way to look at this. If you plot this graph, 3 over x, alright, and you try to find the area under this graph starting at 1 and all the way to infinity, in the end this area is going to be infinitely large. Alright, it diverges. Okay, so that is the answer for number 1, diverges. Now let's try number 2. Let's take a look at number 2 here. The first thing we notice is this. we have the boundaries that is infinite, and this is lower bound, so definitely improper. The problem happens at the boundary, so this is type 1. Type 1, and it's the lower bound, so this is type 1 scenario 1. So let's work right here. I'm going to make partition, so this is going to be equal to, so I'm going to try to get rid of this minus infinity from my integrals. So everything is the same, e to the power of 2x dx. Minus 1 here is the same. I get rid of this minus infinity and makes it just a. And then I use this limit to tell myself that a goes to minus infinity. After that, I just need to perform the integration normally. So what I do here is to integrate e to the power of 2x, and I know this is equal to e to the power of 2x, just the same with this constant down here because of the reverse chain rule. And I have to evaluate this at two values, a and minus 1. And here, don't forget the limit. A goes to, approaches minus infinity. Alright, now let's continue. Equal to limit of a approaches minus infinity, and the inside of that is e to the power of minus 2 over 2 minus e to the power of 2a over 2. Alright, the next thing I'm going to do is to distribute limit to each of these terms, and then equal to limit of a approaches minus infinity of, the first one is e, I'm going to move e to the power of minus 2 down to be a fraction, so this becomes 1 over 2 e to the power of 2 minus limit. So what I did here, distribute this limit to each one of these terms. Alright, limit a goes to minus infinity of e to the power of 2a over 2. Alright, let's take a look here. This term doesn't have any a, so this doesn't really matter. Okay, now what about this one? Minus infinity is going to go to here, so this whole term, I want you to think of this. If minus infinity goes to here, this term is going to have a power that is negative. It's going to go to the denominator, right? And it's really large, so this whole term is going to go to 0. Think of this. It's going to be equal to 1 over 2 e to the power of 2 infinity. Think of this. We put minus infinity here. It can be flipped down to the denominator. And since this is really large, this thing is really large, so this kind of goes to 0. So what we have right here is that in the end we have this term, and that's equal to 1 over 2 e to the power of 2 as the final answer. Alright, okay, and that is the example number 2. Now let's try example number 3 really quickly. This one doesn't take long. The first thing I see here, whoa, definitely improper. And the problem is with the boundary, so this is type 1. Upper bound, this is type 1 scenario 2. So let's try to put limit into this this expression. So upper bound, it's about having this limit of b approaches infinity. So up here I'm going to use b instead of infinity, and 0 sine of x dx. After that, I perform the integration normally and integrate of sine x, I get minus cosine of x. This has to be evaluated at 0 and b. And don't forget the limit here. Limit of b goes to infinity. So here I have this limit of b goes to infinity of minus cosine b plus cosine 0. Alright, so cosine 0, this is going to, well, I can distribute this to this term and also to this term as well, but the back term here doesn't have any b, so I don't need to do that. You can erase that. Doesn't have any b down there, back there. So here in the end we have this limit of, well, minus cosine b. B approaches infinity plus 1. Alright, there is no problem with 1 here, but this 1, this is a problem because, as you know, cosine, it oscillates. It doesn't converge to any values. So we don't know what value, what limit of this term is. So this undefined does not exist. This limit does not exist. D and E, because cosine oscillates. And never converges. Never converges. Alright, so in the end we can answer that. For this one, since this is the first term is not defined, we can say that this integral is divergent. Okay, example 1 divergent goes to infinity, right? Example 2 defined, we have this 1 over 2 times e to the power of 2. This is convergent. Convergent means that it moves to a certain value, and that value is 1 over 2 to the 1 over 2 e to the power of 2 here. And number 3 is divergent, but it's different divergent from number 1. It diverges because it never converges to any value. It just oscillates due to the oscillation. Okay. Now let's take a look at one more, and that is example 4. And it's going to be the hardest of these examples. Okay, let's take a look right here. Okay, give me a minute. Okay. So here we take a look at this integral, and we can see that we have a problem with this integral because the boundaries is, the lower bound is minus infinity and the upper bound is infinity. So definitely this is improper. And the problem is with the boundary, so this is type 1. And as you can see here, we have problems at both bounds, upper and lower, so this is scenario 3. So we have to do something different here. And if you can recall, the first thing we need to do is to split the integration here, the integral here, into 2 parts. Alright, so from minus infinity to infinity. So we have to pick a point and split this integral. You can pick any point, but here, what about I pick 0? I like 0 because when it comes to doing the calculation, 0 makes things easier. So I'm going to pick 0 for this case. Now, this integral is going to be to get split into this first one, starting from minus infinity to 0, right here, of e to the power of x divided by 1 plus e to the power of x dx. Okay, now can't just have one, we have to include the other one to complete the integral. The other one starts at 0, ends at infinity, and same function, e to the power of x over 1 plus e to the power of x dx. Now, here we have two improper integrals. Scenario 1 and scenario 2. So what we need to do here is to apply limit to each of these. The first one, limit, and we want to solve the problem at the lower bound, so we make it a. And we need to tell ourselves a goes to minus infinity of e to the power of x 1 plus e to the power of x dx, plus same thing, limit again, but this case b goes to infinity, so we have 0 to b instead of having infinity in here, so e to the power of x 1 plus e to the power of x dx. Now all we need to do is to perform this integration just like we did before. I think I missed something. 2 is missing. Please add that right here. 2, 2, 2, and 2. So looking at this, we have to integrate this term. Maybe we don't know what to do in the first place, so what about we try something very simple? Let's try to use substitution. What about we put this u equal to e to the power of x. Alright, which means that du equal to du by dx equal to e to the power of x, nothing changes, and this means that dx equal to du divided by e to the power of x. And we are going to substitute this into our integrals. So what do we have here? It's going to be a lot of writing. So limit of a goes to minus infinity. A to 0, just the same. But here we substitute u equal to e to the power of x. So this becomes u. This becomes u. Well, what about I leave e to the power of x up here alone for now? You know why. Okay. Divided by 1 plus e to the power of 2x. So this, I'm going to apply u, and that is u square. Right? U equal to that, so u square equal to e to the power of 2x. And I substitute that into here. Now I take care of this dx, and I use this. This dx is going to be equal to du divided by e to the power of x. And that is why I leave this e to the power of x up here alone, because it's going to cancel with this term. Alright, and this becomes just 1. And the same thing is going to happen with the other integral. Limit of b goes to infinity, 0 to b. Here we have, well, I'm doing everything here all at once. So 1 plus u square du. Alright, same as the front term. Now when you look at this, you see a different things. And you might try to use substitution again, but it's not going to go anywhere else. But if you can recall that this has this pattern, 1 over a fraction of 1 over a square plus u square. Right? Integration of this. We have seen this kind of pattern before, and that is one of the formulas that we learned that is related to arcsine, arctan, arcsecant, right? And if you can recall, this is the one with the arctan. This is going to be equal to, well, we can go right with the with our work here. So here we have this limit of a goes to minus infinity. Integrate this, we get arctan of u. Okay, and this has to be evaluated at 2 points, a and 0, plus another one, same thing, limit of b approaches minus infinity, also arctan of u, evaluated at 0 and b. Now we cannot leave u in our expression like this because in the beginning we have x, so let's substitute e to the x back to u. So here we have this limit. I hope I have enough space to work on this one. Okay, what about I work on this? This u, I am going to substitute e to the power of x back, e to the power of x. Same here, e to the power of x. Okay, so now all we need to do is to plug in the numbers. So here a approaches minus infinity, and here we have arctan of the first term, e to the power of 0. That is going to be 1, plus minus another term, arctan of e to the power of a. Okay, now plus limit of b approaches minus infinity. Oh, I'm sorry, no, not minus, positive infinity. Here we have arctan evaluated at b, e to the power of b, minus arctan evaluated at 0, and that is going to be 1. So all we need to do is to distribute this limit to the one with the a right here, and this to the one with the b. So let's put everything together. So we have this limit of a approaches minus infinity. Well, here I'm going to put minus in front. And that's going to be arctan of e to the power of a. Okay, now here this one, I have this plus arctan of 1. Nothing changes. Then I have this limit b approach infinity. b approaches infinity of arctan of e to the power of b, and this one, the back term, nothing changes, minus arctan of 1. And as you can see here, this arctan of 1, they are going to cancel with each other, plus arctan 1 and minus arctan of 1. Now let's take a look here. This minus infinity is going to go into here, which means that the inside term is going to approaches 0, right? E to the power of minus infinity, which means that this is going to approach 0. Okay, now inside of here, infinity is going to go to b right here, so the inside of this arctan is going to go to infinity. So I'm sorry about the space, but I'm going to continue right here at the top. So this is going to be equal to arctan of 0 plus arctan of infinity. And as you can see here, the angle that is going to make tan become 0, and that is going to be when the angle is 0. And the angle that makes tan goes to infinity is going to be when the angle is pi over 2. And as a result, the final answer for this one is going to be pi over 2. Once again, this arctan of 0 is 0, and arctan of infinity, this is pi over 2. Alright, so for this one, I'm sorry for the mess, but the final answer is pi over 2. Okay? Alright, so we have 4 examples for the type 1. Let's take a look at the type 2 here. I'm going to try to make this as quick as I can. I'm sorry for the long explanation on some of these examples. So let's take a look at type 2. Now let's take a look here. Type 2, if you can recall, this is about the problem with the function itself. Fx becomes undefined at some point. Alright, so that is the main thing. The problem is going to happen with this f. Now let's take a look at what can happen here. Once again, we have 3 scenarios. Scenario 1, the problem is going to happen when we try to evaluate f at the upper bound. Alright? This is scenario 1, upper bound. F becomes undefined at upper bound. Scenario 2, f becomes undefined at the lower bound, or at a. Lower bound, or okay, and scenario 3, f becomes undefined at some point between a and b. Right? We call that point internal point right here. So f is going to be undefined, right? F going to be undefined at point D, and this point D is just some point between A and B. Okay, so 3 scenarios that can happen here. So what do we need to do? What we need to do here is to put limits in again. So let's take a look at scenario 1. So here we used to have this. Well, I'm going to put a and b just before. Fx and dx. But in this case, this b is going to be a problem. Alright? So, since this is a problem, we cannot put this value right into the integral. So we have to do something with that. So in this case, let's change this b to something else. Alright, so we are going to change this b to, I would say, c. And let's take a look here. This whole range from a to b. Alright, and the problem in the first scenario happens right here. So we cannot just integrate right at this point. We can only integrate very, very close to this point. Alright, so we're going to make this c very, very close to b. And as you can see here, it approaches from the left. So the limit that we need to put in here is going to be limit when c approaches b from the left hand side. Don't forget this minus side. Alright. Okay, now let's take a look at the scenario 2. The problem happens at a, the lower bound. So in this case, the problem happens here. And we want to try to perform this integration. Want to perform this integration from a to b. And everything else the same, dx. Okay, now we have a problem with this one, with this a. So which means that we cannot put this directly into our integral. So we have to do something with that. So here we are going to put something else. I'm going to use d. Alright, so it's going to be very, very close to this a point, but we are going to approach this point from the right hand side. This d value is right here, so close to a, and the c is so close to b. So in this case, I have to put limit here and tells us that, and tell myself that this d is going to approach to a, but not at a itself, because function is not defined at a. So, and this is approaching from the right hand side, so this must have plus sign right here. Okay. Now, scenario 3. If this function is undefined at some point between a and b, so it could be this. Let's say that this point D is right here. Alright, so in this case we are going to have to split the integrals into two parts like we did before. So first thing, we are going to perform the integration from a to d. So here we are going to split the integrals to this from a to d, and everything is the same, fx dx, plus another integral from d to b. Alright, fx dx. But now let's take a look at the problem that we have here. fd is undefined. So the problem is this and this. So in this case, we have to put something else right here instead of this, just like we did up there. Alright, so what we need to do is to do something with this. Well, what about I leave it right here, the one with the problem? This d is a problem. Okay, but if you take a look here, these two integrals that we are looking at is very similar to what we have in scenario 1 and 2. Alright, so this, the first one, the ones that has a problem is up here, which is the same as scenario 1, the upper bound. So this is scenario 1, and the second integral has a problem down here at the lower bound. So this is scenario 2, which means that we can combine scenario 1 and 2 right here. Okay, now, alright, let's use that. Here, this is going to be equal to, everything else is the same, a and fx and dx. Here, I'm going to use, what should I use here? I am going to use C1, alright? Just like up here, but add 1 to that. I don't want the notation to get confusing, so this, I'm going to put C1 right here. C1 right here, and we have this limit, just like above. This C1 approaches D from the left-hand side. Okay, now another one, plus integration of, well, let's start with the ones that doesn't have a problem. So we have this b right here, fx and dx, and the one with the problem, I'm going to put c2 here, c2, and here we have to put limit right here. C2 is going to approach this d value from the positive side. All right. Okay, so let me make a box here. Scenario 1, the problem is function is undefined at the upper bound. Scenario 2, your function goes undefined at the lower bound. This at the lower bound right here. The first one is at the upper bound. Okay, and for the scenario 3, the function goes undefined somewhere between the a and b, so you have to arrive at this form. You have to split your integrals into two parts right where it has a problem, right at d. Okay, and after that you just need to combine the scenario 1 and 2 together, and of course we have this scenario 1 for the first integral and scenario 2 for the second integral. Alright, the best way to understand this is to work on some examples. So let's work on 2 examples, and that would be it for this lectures.